Welcome to TD Physics. We're taking a look at how light bends, also known as refraction. So there are two versions of learning how refraction works. One is qualitative, which generally means get a fuzzy feeling for what light does under certain circumstances. And there's a quantitative one where we work with Snell's law and some math. So we're not going to be doing any math on this one. This is just the fuzzy feeling of physics. And we're going to start with what happens when you shine laser light from air, here represented in white, into water, here represented by blue. So to start off, if you want to work with this app yourself, you can find it at PHET, P-H-E-T, and you add the word refraction into Google, and you will be able to find that. Try to remember to put a link in the description. So here we go. So first of all, the first thing you learn when you play with lasers and light is that if you shine light along this dotted perpendicular to the surface, physicists call that the normal, you'll discover that light doesn't bend, it goes straight in. However, when we take that light and we move it a certain number of degrees away from the normal, so this we would call our angle of incidence. And in our math unit, we'd have a theta, that's a fancy Greek letter, and an I. You'll notice that as that angle increases, we actually end up, here I'll grab a protractor from off screen and throw it on here. So here we're coming at 10, 20, 30, 40, 45, let's see, and a smidge degrees. Here on this side is coming out at 10, 20, 30 degrees, which means that our light, instead of traveling straight through, and I can make that appearance if we didn't have water here. So air to air, there's no bending. So it would go straight through. But over here, we're going to find that it bends closer to 30 degrees. So we would call this bending towards the normal. And hopefully you can appreciate that no matter what angle we shine this at, while there may be increased glare, there'll always be some light that is coming into the water right here. Now, what happens if we reverse this? Now, in class, we would simply take our laser and move it to the other side, but I can't do that with this app. So what I will do is instead return my laser to 0 degrees. I'll even toss my protractor off screen here. And instead what I'm going to do is move this to where the water setting is, and we'll move this side to air. So in a lab, you'd have a semicircle of, like a dish, a semicircular dish of water, or perhaps a semicircular prism of plastic. But what we see is that there's a common theme, that there's a special angle. At 0 degrees, you have no light bending, no refraction whatsoever. And so when we come from here and we make this bigger, so we've got an angle of incidence right here, and our angle of refraction is down here in the air. And you'll see that our situation has reversed. Our angle is now greater. Out here, our angle of refraction is now greater because the ray of light is bent away from the normal. And before, we can move our laser anywhere around in the air, and it would always get into the water. But we're going to find a special circumstance here. The greater our angle becomes, something special happens about right here. And this is when our angle of incidence becomes a very special angle. And I've reminded that everyone in class needs to be sure to remember that there's a very special angle, and its name is called the critical angle. So this becomes the critical angle here, our angle of incidence, when our angle of refraction becomes close to 90 degrees in the air. So if we increase the angle by a tiny fraction of maybe a couple degrees here, suddenly the light is trapped inside of the water and can't get out. We call this trick total internal reflection. So all of these angles are greater than critical angle. And in our lab, what we should have found is we did this very carefully. Mathematically, we'd find out the angle is actually 48.6 degrees. And here, experimentally, we find out that it's approximately that as well. So as we approach 50 degrees, the light can't get out anymore. And this is going to act like a mirror. And we use that for many applications, particularly in high-end optics where you can't afford to lose any light. So for example, cameras or telescopes. So quick review, if you're going at 0 degrees, your angle of incidence and your angle of refraction are both 0. If you're in water trying to get to air and your angle is less than critical angle, your angle of refraction is going to become greater. It bends away from the normal. There's a point here where it becomes the critical angle, and that's when we're going to see the light stops getting out and entirely becomes a reflection. And so this is called total internal reflection. And then finally, a review of back to the beginning. If you are in the air and going to water, 0 degrees is still 0 degrees, and any angle bigger than 0 will always result in an angle of incidence that is going to be greater than your angle of refraction because your laser light is going to bend towards the normal. So that's a quick review of what we've been learning about qualitatively. And if you want to work on the numbers of Snell's law, there's another video to review for that as well. Thank you for listening. Catch you later.